बट हम लोग को रेज हैंड का ऑप्शन है।
No, you can just sit.
Sure. Yeah. Hello. Can you hear me? Please raise your hand. Good afternoon, everybody. Now we will start our poster session. That is 1B, and we request all the presenters to be online from 1400 hours to 3. So if someone is not present, we will move to the next presenter. So our turn will come. So you have each presenter will get 2 minutes to complete either our presentation. After 2 minutes, first bell will ring to alert you within next 1 minute with another bell. After 3 minutes, session will be taken over by our judges. I request all presenters uh, from poster number CP0101 and I request the first 5 presenters, that is CP0112, to raise your hand so that we can add them. Or they may also write in the chat box about their and poster number. Just we will start in few minutes. The first 5.
Are we audible?
Yes.
Yes, no? Okay. Hello, I'm Sridhar here. When are we starting?
With portal number CP107. Kindly start.
Chatting with home.
With that chair, that host, that B host, the NLS-30 auditorium B. It is auditorium B. They're sitting there. Their hand control room is there. So they will move the slides also. So
Hello.
Mr. Smith, please start.
Hello. Hello. Can you hear me? Hello.
yeah, we can hear you.
Okay. Okay. Can I start?
Yes,
Hello.
please.
Yes, please.
Yeah. Actually, in this paper, we have presented the development of engineered high pulse energy pulse NDR flash lamp pump laser system for yeah for welding and cutting application of metal and alloy with minimum heat affected zone and shrinkable distortion. In this system, we have used multi-rod linear resonator because for power scalability, we single rod is actually uh, limited to thermal fracture limit. So we have used multi-rod and the multi-rod design is also very simple and more efficient. So in our hello, can you go for a second slide? Hello.
Second slide.
Yeah, yeah. In this system, we have used actually, in this system, we have used two identical ceramic reflected pump chassis in a linear resonator in rod imaging configuration. Both the pump chamber have Nd:YAG rod and two krypton filled flash lamps placed in a close coupled yellow glaze diffuse reflector, and the system contains Nd:YAG rod of 8 mm dia and 160 mm long, and which having 1.1 atom% doping. And in the krypton pump filled flash lamp having a 5 kilowatt average power in each flash lamps. For full range of pump 20 kilowatt, we pump, and the optimum value of D for found to be 35 mm for the plain resonator. And this system is having equipped with a 3 time shared optical fiber ports for remote material processing. Can you go in the next slide? And as laser output power varies linearly with the input power for whole range of 20 kilowatt of power, in this system we get 5.34% of electrical to optical efficiency, and as the maximum average power of 1068 watt at 4 millisecond pulse width and at 24.5 hertz we get. And as you can see that the laser output varies linearly with the input pump power up to 20 kilowatt, and we get 1064 watt power at 20 kilowatt input pump power. And in the figure 4, you can see the beam profile. We get at maximum pump power, we get beam quality factor around 65, which is good enough to couple in an optical fiber of 600 and 400 micron core diameter, having 0.22 numerical aperture for remote operations. And we get maximum pulse energy 567 joule at 40 millisecond pulse width. As you can see in the figure 5, we get maximum 567 joule energy. So with this system, we have cut 30 mm of SS, and we have welded niobium 4 mm thick niobium with this system. and with we can cut up to 40 mm of SS and 6 mm welding of SS.
आवाज जा रहा है.
Hello.
Your presentation is over?
Yeah, my presentation is over.
So you told that it's a doping percentage of 1.8%.
No, it is a 1.1 atom percent NDR.
1.8%. If you increase the doping percentage, what is the effect on the output power or a beam quality?
Beam quality will deteriorate.
And what about the output power?
Output power also we cannot pump more than that because it will have a more thermal lensing effect. Then resonator will go unstable.
What about that thermal induced birefringence effect? Have you observed?
Yeah, we have observed it.
Okay, sir.
I have one question. You have mentioned some imaging technique in that poster.
Yeah.
So what is that? What you are using there?
We are imaging one rod of principal plane to the another rod of principal plane.
Why you are doing so?
Actually, to operate in a stable region and reduce our aperturing losses.
Aperturing losses from where?
From rod faces.
From rod faces.
Yeah.
Is there any other advantage or this thing with this imaging technique?
Actually, we operate with this. We have found out when we have used different D value for, and we found that this is the optimum one, which we can get linear output up to full power range.
Okay.
So,
Yes, sir.
questions are answered, sir. Shall we move to next sentence? So, our next poster will be presented by Sivaprasad Sahu. His poster number is CP0102.
Hello, Sandeep, can you hear me?
Yes, we can hear
Thank
you.
you. Thank you, sir.
Shall I start?
Yeah, start.
Okay, good afternoon, everybody. I'm Sivaprasad Sahu from BARC. So today I'm going to present a novel laser pumping technique that we can go to the next slide directly. That is called dual pumping technique, in which we have increased the efficiency of the laser almost twice. Please proceed for the next slide. Okay, so in this technique, as compared to the conventional pumping technique, the gain medium is pumped with a laser beam. So, but in which the output energy is limited at higher pump pulse energy due to ground state population depletion. But we have developed a novel pumping technique in which instead of a single pump pulse energy of higher energy, we have used distributed pump pulse energy. That means the gain medium is initially pumped with a pump pulse energy of low energy, and the second pump pulse is applied just before initiation of the laser pulse, that is at the cavity buildup time. So what happens, the population that depleted during this cavity buildup time by the first pump pulse are again repumped to the upper laser level system and leads to enhancement of the output laser. So you have applied the technique in a polarized based chromium phosphorylate laser resonator cavity. And hello.
Hello.
Sir, am I audible?
You are audible, but PPT is changed. Okay.
Okay, so in this pump, we have applied this pumping technique in a chromium frostoride polarization-based laser resonator cavity, in which the output energy of the laser has doubled compared to the conventional pumping technique. So this technique suggests that instead of operating the laser at higher pump pulse energy of a single pulse, we can use multiple beams. So which will help in enhancement of the laser efficiency. Along with that, it will allow us to pumping the crystal at higher energy due to the higher damage threshold, and it will also suppress the other detrimental effects. Next slide, please. Next slide, please. Okay, so this is the experimental setup in which the pumping, that is NDX laser, is divided by two parts. So the upper part is the we called it as pump beam, and the lower beam is the control beam. So the pump path is fixed, but the control path is changed. We have changed the path of the control beam so as to provide variable delay between the pump and the control pulse. And this cavity consists of this resonator cavity consists of the mirror M1, M2 with IPVS. The spot size for both the pump beams along with and the polarization of both the beams are remain same during the operation. So what we have seen, we have varied the delay of the control pulse, and we have studied what is the effect. So next slide, please. So you can see this is the output versus input energy. That means in x-axis, this is the total input energy, which consists of a pump pulse energy of 5 millijoule, and the control pump pulse energy is varied. The black is for single pumping, and the red curve is for dual pumping with 0 nanosecond. That means in 0 nanosecond, the path for both pump and the control pulse is same. We can see both the curves are overlapping. That means for dual pumping of 0 nanosecond, it's exactly follow the single pumping. However, if we increase the delay, when the delay between the two pulses is 22 nanoseconds, you can see the slope of the curve is increases, and also the value is higher. At a higher total input energy of 15 millijoules, the output energy is 1.35 times more than the conventional single pumping technique. And if we increase the delay to 34 nanoseconds, we can see the output is almost 2.1 times higher than that of the conventional pumping technique. So in this case, our pump pulse energy is 5 millijoules, which corresponds to a build-up time of 34 nanoseconds. So when the build-up time matches with the delay between the pump and the control pulse, what happens? Those population that comes to the ground state during the build-up time are again repumped, which leads to enhancement of the laser efficiency. You can okay. So to know whether where is it exactly at the build-up time or not, this shows the ratio of the output energy in dual pumping to single pumping with respect to build-up time. See, for different pump pulse energy, we have always to vary the path length, and this is a very difficult job, because again the experimental system has to be misaligned. So we have used the chromium frostoride laser in polarized laser-based cavity, in which allows us to continuously vary the build-up time. So for that, for a
You have to stop.
I request the judges to ask questions, please.
I have a question. Mr. Sahu, you are saying that the build-up time is the limiting for the delay between these two pulses. If you delay further, then what will happen?
delay further.
Yeah.
Yes, sir. This curve shows if you will delay further, that means the extraction efficiency is not more, because sir, what happens after the build-up time, the cavity itself has some cavity decay time. So in this case, it is around 3 to 4 nanoseconds. So that means this repumping effect, which happens because after the cavity decay time, the pulse will come out. So this is just like some single pumping with two pulses. We will get two output pulses.
So in this case also, you are getting the same temporal profile as with zero delay.
Yeah, yes, sir. In case of the dual pumping, the temporal profile, our pulse width is increased by 2 to 3 nanoseconds, because in zero delay it was around 20 to 12 to 13 nanoseconds, but in this double pumping it increased by 2 to 3 nanoseconds only. And when it is away from the build-up time, we are getting two pulses, which is as like a conventional single pumping technique.
Okay. Basically, you are pumping two pulses like that.
So
Okay.
in this case, sir, along with efficiency, we can pumping at higher pulse energy also.
Okay.
This is separated pumping, what other effect you will have? What other advantage you have?
Sir, this will also help for decreasing the excited state absorption, which I have not presented here. Means if you see the excited state absorption at higher pump pulses will be higher, because pump pulse energy is higher. Also, the upper level population is higher. If we with this distributed pumping technique, dual pumping technique, the effect of excited state population absorption will be lower. This also helps in enhancement of the laser efficiency.
I have a question.
Yes, sir.
How do you avoid damage to the crystal?
Pardon, sir.
How do you avoid damage to the crystal?
Yes, sir. Yes, sir. So a crystal has some damage threshold. So for a particular pump pulse, let's say it's some X millijoule. Let's say it's
Yes.
15 millijoule. Now what will happen? I will apply two pump pulses. One is 5. So when one is 5, the other I can go up to 15. That means I can operate the crystal at 20 millijoule instead of 15 millijoule, as an example I have given. So in that way, because the damage threshold is some value. So when I'm using dual pumping, I have distributed the pump pulse energy. Hence, it will allow to pumping the crystal at a higher pump pulse energy.
So you are basically temporarily distributing the energy.
Sir, exactly, sir, exactly. We are temporarily distributing.
Sorry to intervene, but there is a request that both the presenters as well as the judges, they should maintain the time, because we are really hard pressed against time. Therefore, I also request that the presenters should be attentive. There will be a bell ringing at the end of 2 minutes, and there will be another bell at the end of 3 minutes. After that point of time, the control will directly go to the judges and take 2 seconds to wind up your time. And then you should ask the question. Please, judges also, I request you that please limit your question and answer session for around 2 minutes or so. Actually, we can't help. I mean, it's very nice that we are getting this platform to interact, but we can only do this much in this online proceeding. So now we will move on to the next participant. So the next presentation is Utpal Nandi, Arakat, and the poster number is CP0105. Are you there, Mr. Utpal Nandi? So we are starting your presentation, and you can just, as soon as the slide appears on your screen, you can start the presentation.
Okay. Am I audible? Can I start?
Yes, sir.
Yeah. See, the title of my talk is Study of Output Characteristics of a Q-switched CW/CO laser with mirror rotation. Obviously, we are talking about rotating mirror Q-switching. You know, any laser, CW laser, will normally have a curved total reflector and an output coupler. Now, if you rotate the curved mirror, then you can produce a giant Q-switch pulse. Can I have the second slide, please? Yeah, Osgood was the one who first carried out this Q-switching, rotating mirror Q-switching in a CW/CO laser. And what he found, that it was possible to generate multi-kilowatt microsecond duration pulses in a composite pulse. Why I am saying it is composite? It is because this composite pulse consists of hundreds of pulses which represent various rotational lines in vibrational modes. You know, CO has a many levels of vibration levels, and we can get rotational transitions from vibrational band 22 to vibrational band 5. Actually, I have actually, this is a theoretical paper. I have developed a model which can carry out this which can study these output characteristics. So what I have done, I have varied the frequency of rotation of this mirror for these following values: 80 hertz, 100 hertz, 200 hertz, 250 hertz, and 300 hertz, 320 hertz. And each time I am measuring 4 parameters. What is the peak power of the composite pulse? What is its duration? And how many number of lines? You know, this composite pulse is consisting of a large number of lines. So how many lines are lacing? And I am also trying to find out which is the strongest line. For example, when I operate at 200 hertz, 9P10 is the strongest line, which gives about 78 watts. So can I have the second slide, please? So when you rotate a mirror, what happens that most of the time the two mirrors are not aligned. So the Q is very low. And when the mirrors come into alignment, Q becomes very high. But see what happens, this is a mechanical switch. It has a certain way of changing this Q. Now every laser has a certain kinetic time, and that depends on the gas mixture, pressure and temperature. We are using CO 0.2 torr, helium 6 torr, and the temperature is 165 degrees. For this system, we saw that 200 hertz is the 200 hertz is the best. It gives the best result. We get 5 kilowatt pulse and 750 nanosecond pulses and 173 lines operate. Can I have the next slide, please? See what happens that actually my theoretical model is presented in Journal of Optics and Laser Technology, February. Please go through it to understand the various aspects. But see, a very big application of this laser, because of this number of lines which are lasing, we can put this laser, focus it into a crystal which is called zinc germanium phosphate, and we can generate additional lines. And suppose 100 lines are lasing, they can generate, it is lasing from 5 micron to 6.4 micron. So it can produce a sound frequency generation from 2 micron to 3.2 micron. And 100 lines, if they operate 2 by 2, then you will see that 5,000 new lines are generated. So this is an application on which many people are working. So here you see the number we can get a figure by this study. If n is the number of lines lasing and if p is the power of the maximum strong line, if you multiply this, that gives a good figure of merit. See, because see, if n is the number of lines, new lines generated is n square by 2. So it is proportional to n. And if the peak power of the strong line is very high, then the nonlinear generation process is very good. So our study shows that again 200 hertz is the best operating frequency for this application. Thank you. That is all. Any question?
Hello,
Yes.
I have a question. See,
Yeah.
it is multi-line, but as you said, this can be used for nonlinear conversion. Now,
Yes.
if your application requires a particular wavelength, so how will you choose the combination for nonlinear conversion?
No, in that case, you cannot operate on multi-line. Then you have to have a grating. Instead of this curved mirror, you have to have a grating and you have to tune it. If you
No,
want
but
a particular...
if you use a grating, if you use a grating, then you will select only one line.
Yeah.
And so you cannot have some frequency generation or things like that. Then it will be only frequency doubling output, or so there will be some limitation, isn't it?
Yeah, that is right. That's right.
My
Yeah.
second question is, you said if the speed of rotation of the mirror is too slow or too fast, then the laser would not reach the optimum level.
That is right. That is the study. And we saw that for this system, where we are using CO 0.2 torr and helium 6 torr, 200 hertz gives the best operation. That is the study. This is what we have studied.
Okay. Okay, bye. Thank you.
Thank you.
So we move on to the next presenter. And the presenter is Mr. Avadit Kumar from Maharashtra. 0106.
Hello. Hello.
Yes, sir, you can start. If you can see your first slide, you can start.
Okay. I'm audible to everyone.
Yeah, please start.
Okay. So good afternoon, everyone. So in this piece of work, we report on the development of monolithic 1 kilowatt single transverse mode all fiber YB.CW fiber laser. That is ytterbium doped CW fiber laser at 1080 nanometer. So worldwide, monolithic fiber, high power fiber lasers are widely adopted as a laser source for industrial application as well as for rock and concrete drilling in natural gas and oil exploration and also in defense applications. For all fiber lasers, two major configurations are used for achieving high power fiber lasers. Like one is oscillator configuration and another one is MOPA configuration, that is master oscillator power amplifier configuration, which amplifies the seed signal from the oscillator stage. So in this direction, in our lab, we have developed 1 kilowatt all fiber single transverse mode YB doped CW fiber lasers. That is pumped with a laser diodes of 950 nanometer. And in the right hand side, you can see the tabletop setup of 1 kilowatt YB.CW fiber laser engine. So can we go for the next slide, please? Uh, so here you can see the schematic of that fiber laser engine. So here the 200 watt 7 laser diodes are combined using 7 into 1 fiber optic pump combiners, and here the HRFBG and LRFBG forms the grating mirrors between the YB doped fiber lasers, and the output is coupled to the cladding power strippers that reduces the unwanted cladding power in the cladding, that is in the output end. So the output of the cladding power stripper is connected to the QBH fiber delivery fibers. So here the major problem is in this setup is splicing losses and the recoating of the splicing joint, and further the heating of the cooling of the different joints of the this fiber laser is one of the major problem in this fiber laser setup. Can we go for the next slide, please? So here the results for we have achieved a power of 1 kilowatt by pumping 1300 watt pump power with and achieve an optical to optical slope efficiency of 74.4%, and the measured beam quality is nearly diffraction limited, that we achieve mx square 1.3 and my square is 1.24, and the spectrum is also at 1080.25 nanometer with FWHM 1.5 nanometer, that is governed by the FVG mirrors. And we have operated this system for more than half an hour continuously, and the power is stable within 1.5%. And now we are in the direction of converting this tabletop setup into a handy instrument. So this is what I am here to present. And
Over to judges.
I, I have one question.
yes, sir.
What is the change you have made in this setup as compared to the previous one? Last year you reported 500 watt from the similar system. So what is the major
Sir,
breakthrough?
sir, major changes are here. Other one is the pump combine the fiber optic pump combiner is 6 plus 1 into 1. So here we have combined the 200 watt diode laser and another component like cladding power stripper we have added in this
So
system.
basically you have increased the pump power, and this is why you are getting
Yes, sir.
higher power. So
Exactly. And the another change is like the we have very carefully maintained the splice joint between the HRFBG and YB dope fiber.
Agreed. So that
Because at
means,
high pump power, this joint got burned.
okay, fine. But if you
Hello?
keep on increasing the pump power, if you instead of 200 watt, now if you use 250 watt or 300 watt laser diode,
Yes, sir.
you can scale up further, right?
Yes, sir. We can scale up to further. There are report up to 5 kilowatt of laser power from a oscillator configuration also.
And second thing, why you are not pumping from the other side also? Because this can,
Yeah, we can. Yes, sir. Yes, sir. We can do also that thing from pumping from the other side. But right now we are able to achieve in further like for going for 2 kilowatt. We can adopt that topology also.
okay, okay, fine, very good.
Thank you.
I have a question.
Yes, sir.
You mentioned about very good special quality of the beam. May I also ask you what was the spectral quality of the beam? Hello? Hello? Hello?
So,
Can you tell me what was the spectral quality?
expect actually, sir, this the output from the laser is nearly Gaussian beam.
No, that is the special quality that I know. But
Yes, sir.
do you have any idea about what kind of spectral quality the beam had? How was the frequency stability of the laser? You are not interested in that, is it? Okay.
Exactly, sir.
Actually,
Okay.
sir is
Shall we
asking.
move to second?
Okay, move. Okay.
So our next presenter would be Lal Bahadur Rana from RRCAT, and his poster number is CP0104. So Mr. Lal Bahadur, please start presenting.
Yes, sir. I am audible.
Yes, you are
Yes,
audible.
yes.
Okay, sir. Good afternoon to all. My topic is design and development of mechanical system for carbon monoxide laser. So the object is we report the design and development of mechanical system for carbon monoxide laser. AutoCAD and Solid Edge software were used to design and generating manufacturing drawings. Vacuum chamber having rectangular shape, which operates at a pressure of 1.01325 into 10⁵ Pascal, that is atmospheric pressure. Analytical design and buckling failure analysis of vacuum chamber were carried out. Minimum achievable leak rate were estimated for the O-ring groups with best achievable surface finish. So introduction is CO laser offers enhanced capabilities for industrial and medical applications. It enhances the processing characteristics in application ranging from glass, ceramic, film cutting, and drilling. CO laser output at a wavelength of approximately 5.33 micron. There is a stronger absorption at 5 micron in certain plastic films, polymer, and water, as well as some of the dielectric materials and copper oxides used in PCBs. The vacuum chamber has been manufactured and tested for functionality and its vacuum integrity and finally assembled at ARCAD. So challenges for developing CO laser. No previous experience in the field of CO laser. System leak rate and leakage of poisonous CO gas. Low temperature cooling. No idea of current density where CO dissociation will take place. Discharge tube size selection. Moisture content will be kill the laser action. So please next slide. Design, development and testing. The vacuum chamber and other optical mounting components were designed and manufactured with the help of analytical calculations using ASME code and other vacuum system design formulas. The vacuum testing of CO laser system were carried out of the vacuum capability of about 1 into the power minus 4 millibar. The leak rate was measured by the helium leak detector to ensure the allowable leak rate about 1 into 10 to the power minus 9 millibar liter per second. So here is the formula for thickness calculation. That is, we have taken from ASME code. T minimum is CZA upon 10 root P by F, where A is the short span of non-circular head in mm. In our case, it is 120 mm. B is the long span of non-circular head in mm, that is 285 mm. C is a factor. 1 second. Sorry, I just want to increase it. Okay. So C is a factor depending upon the method of attachment to cell. That is, we have taken 0.7. P is the design pressure in kgf per centimeter square. That is 1.033 kgf per centimeter square. F is the allowable stress value in kgf per mm square. That is 7.75 kgf per mm square. So it is taken from the Analysis 304 in the SME code section 2. So here we can see the photographs
Mr.
of.
Rana, your time is over. Over
Okay,
to
sir.
judges, please.
Okay, sir. Just. This is the photograph of this developed system, and this is the vacuum chamber. And here is the demonstration of CO laser beam on wooden block. That we have measured the power. And sir, next slide. Next slide, please. So the Z value can be calculated.
It's 4 minutes almost.
Okay, sir.
Okay, Ranaji, can you tell me what are the gases you are using for this CO laser?
Sir, gases are helium, nitrogen, O2 and CO.
What is this ratio of these gases?
Sir, 1 minute. Sir, I have to conclude just please. The mechanical system has been developed for the carbon monoxide laser, the vacuum chamber, and here the laser has been demonstrated and initial CO laser power measured about 5 watt in the single limb diffusion cooled discharge tube. The mixer is, sir.
Judges, please ask your questions.
Sir, Hello, sir.
Rawat sir, please ask the questions.
सर रावत सर कुछ पूछना चाहते थे मिक्सर रेशियो जो है
Mixture ratio, can you tell me the mixture ratio?
सर मिक्सर रेशियो इज sir mixer ratio is just here the mixer ratio is CO, nitrogen, helium and O2. So here is 1:7:28:0.7. So O2 gas is 0.07 and CO is 1%.
It is also moisture content is also required there, or no?
Yes. Moisture requirement is more than 100 or 200 ppm is kill the total laser casing. So we have used for moisture analyzer in this system.
Okay.
And measured and maintained to less than 200 ppm.
Okay, thank you, Ranaji.
Okay.
So shall we start the next one? So next presentation will be from Mr. Bhupnesh, and his poster number is CP0109. Please start presenting.
Hello. Good afternoon, everyone. Can you hear me? Hello.
Yes, you are audible.
You can start.
So I will be presenting on the development of a 5 watt narrow line width all fiber multi-stage amplifier setup at 1550 nanometer. Now we are calling
3 minutes.
Okay, we are calling a laser system having line width less than 1 megahertz as narrow line width, and these system require in many applications. For example, precise interferometric measurements, metrology, high resolution spectroscopy. So most of these mentioned application require laser power more than 1 watt. Now obtaining such high power directly from oscillator with a narrow line width is slightly difficult. So better option is MOPA configuration. Now this fiber amplifier can be a solid state laser amplifier or this fiber based laser amplifier. We are preferring fiber-based laser amplifier, as they are having a many advantages over the solid state counterparts. Now the main problem of the problem associated with the fiber amplifier are a generation of AC, spontaneous Brillouin scattering, and heating. Now which were minimized through proper simulation before the actual design, and proper cooling arrangements were made. Next slide, please. Next slide. Yeah, this is our experimental setup. So we have a sheet source and we have a preamplifier which is based on single mode fiber, RBM doped fiber, and we have two amplifier stages, amplifier stage 1 and 2. Now this preamplifier amplify the seed power from 10 milliwatt to around 60 milliwatt, and amplifier stage 1 amplify from 60 milliwatt to 1 watt, and our final amplifier stage 2 amplify from 1 watt to 5 watt. Now, in the insert, we can see the photograph of actual setup where major components are shown. Next slide, please. Now, I will summarize the results. Now, it is clear from the first data that our output power is increasing as we are increasing the pump power, and corresponding to around 37 watt, we got around 5.2 watt output. And this second data shows the output stability of the final output. It is clear that the output is quite stable and fluctuations are within 0.01%. And the third figure shows that our output spectrum is peaked at 1550 nanometer, and there is no contribution from pump, which is at 976 nanometer, and ASE. And in conclusion, we can we have developed an all fiber multi-stage amplifier using RBM code of Gen fiber for amplification of a fiber coupled sheet source from a level of 10 milliwatt to 5 watt at 1550 nanometer with line width less than 1 megahertz. Thank you.
How do you measure the line width?
Okay, so we are using the self-heterodyne detection technique for measuring the line width.
And how do you measure the ASC?
Okay, for measuring this third figure shows the spectrum of output, and if there is any ASC, it will be shown in the spectrum. And it is clear from the spectrum that since it is peaked at 1550 nanometer and there are no side band around this 1550 nanometer, it clearly shows that there is no ASC.
Okay.
So your line width measurement, you bifurcated the output into two and then heterodyned it.
Yes, sir.
So what was the result in time? How the bit frequency was changing?
Okay, well, like in the bit signal, and we the output from this heterodyne like detection setup will be it is based on these bits, and by analyzing the bit spectrum, we got the information about this line width of lasers.
So in time, how was it changing? Was it absolutely steady in time? What was the fluctuation, variation?
Yes, yeah. There are lots of variation in it is not stable. It is fluctuating, highly fluctuating.
Highly fluctuating.
Yes.
But the maximum fluctuation was limited within 1 megahertz.
1 megahertz. Yes.
Okay.
Okay. So let's move to the next one. Miss Jyoti Sharma from RRCAT, and the poster number is CP0110. Please start, Jyoti ma'am. Miss Jyoti, can you hear us? Please start. Miss Jyoti, you can start now. Can you see the poster?
Unmute yourself if it is muted.
I think we should move to the next to
Okay.
save time.
So
Hmm.
Srikant ji ka join kare. Huh?
Alright.
So let's move to the next one. That is Mr. Srikant from RRCAT. The poster number is CP0111.
Am I audible to you?
Yes, yes, sir.
Yes,
Please
yes.
continue.
Good afternoon, everyone. This is about development of engineered two-arm time-synchronized all-fiber optic front-end system for high-energy NDR class laser. A two-arm high-energy ND class laser is under development at RRCAT, and it is in a MOPA configuration, master oscillator power amplifier configuration, and we require a master oscillator for that. And the fiber optic front-end system is meant for that. That is, it will work as a master oscillator for the high-energy laser. It is based on an all-fiber architecture for obvious advantages, and it is designed to operate over different pulse widths and to serve the typical requirement of energy physics. Next slide, please. Next slide, please. This is a schematic of a fiber laser system. It starts with a CW narrow line width fiber laser, and then we use two stages of external modulation to convert into a pulsed beam. The first one is based on acoustic modulator. Its main function is to reduce the average power without affecting the peak power. The next one is the intensity modulator. It is a lithium niobate based electro-optic modulator. It will be driven by an arbitrary waveform generator, and it will generate the final required pulse width with a required temporal pulse shape. Then, because we require more than one arm, we have used a fiber optic splitter and a delay module to bring both beams synchronized in time at the target. That is the splitter cum delay module. Then we use two independent fiber amplifiers, one for each arm, to further amplify from picojoules to nanojoules. Next slide, please. This is the system is developed in a modular architecture and into an industrial 19-inch rack system. Its specifications are like it works at 1053 nanometers and at a repetition rate of 100 kilohertz, and the pulse width is pulse energy is 40 nanojoules at a pulse width of 3 nanoseconds, and both pulses beams of both arms are synchronized to within a 10 picoseconds. So this system is ready for the integration into the high energy system. Thank you.
I have a question.
Judges, please ask your questions.
Yeah. So, yeah, what is the seed source? Is semiconductor laser diode or?
Seed laser is actually a 2-watt CW laser commercially available. Its inner parts is it will have a narrow line with a semiconductor laser and a CW fiber amplifier integrated into the fiber laser system. That is a commercially available one. It is a 2-watt fiber laser system.
2-watt fiber laser system operating at 1053.
As you said, it is a semiconductor laser and a CW fiber amplifier.
So both are there.
Right.
Okay. And what is the what you had with is with the AOM? You said that it is to reduce the average power.
Exactly, because because you are generating pulses from CW laser. Between pulses, you should have ideally zero energy, zero power beam. But
through the AOM, you are taking that diffracted beam only. So that will be in the pulse also, right? Or highly modulated.
Right.
What was the modulation frequency on the AOM, acoustic modulator?
That is that the driving RF frequency is 150 megahertz.
150. So okay. For intensity modulation, you are using electro-optic modulator.
Right.
Okay. Fine, I think.
Thank you very much.
Okay, so let's move on to the next presenter, Mr. Pradeep Kumar Gupta from RRCAT, and the poster number is CP0113.
Yes, sir.
So, Mr. Pradeep, please start.
Mine is CP01, Usha Chakravarti, 1, 2.
Am I audible, sir?
Yes, you are audible. Mr. Pradeep, please start.
Yeah. So my work is about all fiber passively QCG terbium door fiber laser using fiber optic resonator. So fiber optic resonators, they have several applications such as nonlinear optical devices such as optical switches, saturable observer, etc. So using fiber optic components, a saturable observer has two major advantages. First, they are of low cost, and secondly, their performance does not deteriorate with time, unlike other material-based saturable observers. So only few reports are available with fiber lasers used using fiber optic components like multimodal interference and fiber optic ring resonator. So here I have shown the schematic diagram of our laser setup. So this is a gain medium, and this is found through a fiber coupled laser diode, and this is a polarization controller. This is polarizing beam splitter, and again polarization controller, and the one band pass filter, and a fiber optic resonator. This is a isolator to make the unidirectional recaptive. So please go to the next slide. So now to understand how the fiber optic ring resonator is acting as a saturable observer, we have made a simulation. So here, this is the fiber coupler. So how this FORR image, one of the output port of the fiber coupler is spliced with one of the input port of it. So this is connected. So it acts. So this is how we make a fiber optic ring resonator like shown here. So now, if a linearly polarized light is launched to this fiber optic ring resonator, so this polarization controller makes linearly polarized light to elliptically polarized light. Elliptically polarized light. Now, when this elliptically polarized light is connected to this fiber optic resonator, so it makes several round trips, and in each round trips, its ellipticity, polarization ellipse, is rotates. It rotates and obtains steady state after several round trips, like shown here. So after around 30 round trips, it stabilizes. So uh, we see that the steady state response of this FORR is obtained around 30 round trip. So it corresponds to around 2 to 3 microsecond duration. So this FORR is acts as a slow saturable observer. So by orienting this polarization controller, we again can change the orientation of this polarization ellipse, and when this pass through PBS, we can calculate the transmission of this setup. So it is plotted here. So it acts as a saturable observer in this region. Now by changing the polarization controller settings, we can change the transmission characteristics of the saturable observer. So please go to the next slide. Yeah, these are the experimental results. We obtained QC pulses here, and these are typical QC pulses. And now, with the increase in pump power, the rotation rate is increasing, and the pulse duration is decreasing. This is the typical behavior from any type of QC laser. So this is the QC pulse. Now this is something special. Here, if we see the rise time of the pulse, this is 945 nanometer. 945 nanosecond, and the fall time of the pulse is around 1000 this. So rise time of the pulse is larger than the fall time of the pulse. So this is something unusual. So if we define the pulse symmetry factor by defining this rise time divided by the fall time, then we see that it is always greater than 1. This is different from the typical QC laser, and this is the these laser characteristics. So initially laser operates in CW mode, and after certain threshold of power, it operates in key switching regime. It is also different from passive QC setup where no CW lasing is achieved. So this is all about this passive QC laser setup using fiber optic ring resonator. So I have finished.
Okay, thank you. Let's move to the second, to the next poster. That is
Mine is not
from
there.
Miss Usha Chakravarti from RRCAT. So poster number is
Yes, yes.
CP01
and 12.
Yes. Yes, I am ready.
Miss Usha, can you see the presentations?
No, sir, I can't see the presentation.
So you can start now.
Just a minute. There is some problem, I think. Where is my? I'll start.
Okay, okay.
I'll start. But I am unable to see my presentation. Can I share from my?
It is already shared and seen by
Hello?
the judges also. You can start from your PC itself.
I can start, but I can't see. Okay. I am unable to see the presentation, but yes,
So
but I'll
you can just open in your the file in your PC.
Okay.
But don't
I have
share.
opened it. Yes, I'll start speaking then.
Okay.
Generation of I have done the work on generation of 920 watt of peak power from all fiber acousto-optic Q switch thulium doped fiber laser at 1940 nanometer. The advantage of the thulium doped fiber laser is that it's operating at the I-safe wavelength near 2000 nanometer, and because we are working at 1940 nanometer, it is preferred for the application because at 1940 nanometer, the absorption in water is very high. So in this case, we have generated acousto-optic Q-switched pulses from all fiber acousto-optic Q-switched thulium doped fiber laser. In the next slide here, this is the experimental details. Here we can see the PC is the pump combiner. FBG1 is 99.8% reflectivity fiber Bragg rating, and FBG2 is the output coupler, which is 10% reflectivity at 1940 nanometer, and AOM is the acousto-optic modulator, which is generating the Q switch pulses. TDF is our gain medium, that is the thulium doped fiber laser. So in this case, we have generated 920 watt peak power of the pulses. Here, while generating the pulses, what we have observed that in the single pulse, there were multi peaks were present. So these multi peaks were because of the feedback from the end of the fiber. So when the end of the fibers were angle cleaved, we observed that we could obtain a clean pulse. The spectrum, this shows at 1940 nanometer. If we see, then we have also studied the multiple pulses in the Q-switched thulium doped fiber laser, in which what we have observed, when the on time is very large, that is at about 23 microsecond, we have observed there were 3 pulses. As we decrease the on time from 23 to 21 microsecond, the number of pulses decreased to 2, and we obtained a stable single pulse at 12 on time of the 12 microsecond duration. The multiple pulses were because of the slow switching effect, and optimization of window on time is very much required for the generation of stable single pulse generation in case of the Q switching. So this setup, in the conclusion, I'll say the present setup is suitable as an oscillator at 1940 nanometer, which can be utilized in MOPA configuration to increase average power, pulse energy, and peak power, and which can be used in medical application for surgeries, microsurgeries. Thank you.
Over to judges.
I have one question. What is the average power?
So the average power is approximately 3 watts.
And you said that multiple peaks in the pulse is coming due to the end reflection from the fiber.
Multi peaks, yes sir. Multi peaks were there, yes.
But you have to do anyway angle cleaving to avoid any pre-lasing from the system, right?
Yes. Actually, initially when we started, at the one end we angle cleaved, the output end was angle cleaved, but the other FBG other end was not angle cleaved. So initially, when we were starting the experiment, some multi peaks, which was of the duration of round trip time of the cavity, because the length of the cavity is approximately 6 meter, and those multi peaks were at the duration of 60 nanoseconds. So when we angle cleaved the output end, those multiple pulses were removed.
Okay, I am done.
So let's move to the next poster. Mr.
Thank you.
And PN Krishnaji. Krishnaji, please. Please, your poster number is CP0103. Can you see the poster?
Am I
Please
audible,
start.
sir? Am I audible, sir?
Yes, you are audible. Please start.
Sir, thank you, sir. Sir, in any interferometer, shifts in the interference fringe pattern are due to changes in the polarization and phase of the light beam that is affected by any physical parameter, such as stress, strain, and temperature, and refractiveness of the transverse material. In the present study, the effect of retardance on the fringe pattern of Sagnac interferometer is theoretically analyzed, sir, using Jones matrix. So, as shown in the figure, sir, actually, it is a Sagnac interferometer where we are having two ports. One is input port and another one is the output port. And one beam will travel in clockwise direction and another beam will travel in anti-clockwise direction. Both will meet at output port there where we are having the intensity fringe pattern. Here, in this case, to identify the effect of retardance on the fringe pattern of the interferometer, we had introduced one optical element in one of the arms of the interferometer. Where we known the retardance of that optical element, and by marrying the fast axis of that retardance, we'll see the shifts in the interference fringe pattern. So by means of Jones matrix, we have calculated the entire intensity part. That instant intensity fringe pattern is given at the bottom side, sir, where delta is the part difference between the two beams, and del is the path difference between two beams, and delta is the fast axis orientation of the fast axis, and delta is the retardance, and pi is the fast axis orientation. And next slide, please, sir. Next slide. So in the first case, we had introduced the circular wave polarized light at the input end, sir, with the retardance of pi value, and by rotating the fast axis, there is a shift in the fringe pattern. There is no variation in the intensity. But with the retardance of the pi by 2, we are having the peak shift with the along with the reducing intensity. In the second case, with the elliptical polarized light, we are having both with the retardance of the pi value. We are having the peak shift as well as the intensity variation. Next slide, please. In the third case, we introduce the linear polarized light at input end with the retardance of pi value. We are having the intensity variation, but there is no peak shift. So here in this, so the conclusion is that the variation in the fringe shifts are dominant for the retardance value of pi to pi by 4. Beyond that, the retardance as retardance decreases, the fringe pattern also become minimal. So by observing the pink shifts, we will able to estimate the state of input polarization as well as the retardance offered by the Sagnac loop. Thank you.
I have one question. Here you are giving known amount of retardance, right?
Sorry, sir.
In your setup, the amount of retardance is known.
Yes, sir.
Yes. So how you can decide about the retardance if there is any arbitrary amount of retardance is there from this principle?
Sorry, sir. It is not audible, sir. Sorry.
Well, my point here is that you are giving a known amount of retardance, right?
Yes, sir. With the known retardance only, we had checked the entire part, sir.
So if it is arbitrary, then how you can decide the amount of retardance?
Still, sir, experiments has to conduct, sir. This is basically theoretical analysis only, sir. Actually, with experiment, we came to know, sir, that with arbitrary retardance, sir.
Okay.
By doing the calibration, we will came to know, sir.
Okay.
Yes.
Fine.
We move to the next.
Okay, sir. So
Okay.
next presenter is Mrs. Jyoti Sharma from RRCAT. Poster number is CP0110. Ms. Jyoti, can you hear us?
Yes, sir. Is I audible, sir?
Ms. Jyoti, please start.
Yes, sir. Good afternoon, sir. I'm presenting my work on development of edge cladding of large size antiphosphate glass disc for high energy laser amplifier. Under DA's mandate, RRCAT is developing high energy and high peak power ND glass laser system, which is based on a series of power amplifiers. And for extracting larger laser energies, large size ND glass discs are used. However, because of embargo restrictions, we cannot import them. Hence, CGCRI in collaboration with RRCAT is developing them indigenously. And once these large size ND glass disc is installed in the laser amplifier, then they exhibit certain losses like amplified spontaneous emission and parasitic oscillations, which eats up the gain in the medium and thereby they reduces the extraction efficiency. Also, this loss becomes severe once the dimension of the disk increases. So, the solution to rectify this issue, we can edge clad the ND glass disc on its four edges with the copper dot clad glass. So, this edge cladding requires the cementing of this ND glass with the clad glass. However, this is not a simple pasting. Worldwide, different methods have been explored, and we are doing it using an epoxy-based adhesive. So at RRCAT, we have developed the indigenously the edge cladding of glass size ND glass disc. Next slide, please. So there are certain key requirements which this clad glass and adhesive has to satisfy. First, for clad glass is that its refractive index should be matching with that of the ND glass. We have measured it using experimenting the prism coupling technique. And second requirement is that it should have high absorption at the lasing wavelength. For that, we have measured using the spectrophotometer. There are certain key requirements which our adhesive also should satisfy. First is that its refractive index should be matching with that of ND glass, and for that we have done the reflectivity measurement shown in the experimental setup below. Here the reflectivity from the interface from adhesive and ND glass is measured, and from this the refractive index of the adhesive is calculated. Also, this refractive index should remain stable under the high energy density flash lamp radiation. So we have measured it. Next slide, please. So we have measured these adhesives refractive index after the flash lamp shots, and the adhesive, we can see in this graph that adhesive 1 and 2, they can sustain 1000 number of flash lamp shots without changing the refractive index. Also, the third key requirement of this adhesive is it should be remain chemically stable both under the ambient environment and under the flash lamp fluence. So we have carried out the FTIR measurement, and adhesive 1 shows the no compositional change in both the cases. So based on these results, we have identified adhesive 1 for our cementing purpose, and using this adhesive, we have done the fabrication of the glass rods which has been obtained from CGCRI, and then the grinding and polishing is done at the RRCAT, and finally these cementing is done using adhesive 1 in this UV curing unit, and the one which is shown in this pink glass, that is the final disc, edge cladded disc which we have obtained.
Ms. Jyoti, please wind up fast.
Yes, sir. We have just compared our results with the National Ignition Facility. So our adhesive 1 is almost comparable with that of the NIF. Thank you. Thank you, sir.
How did you check the homogeneity of this single crystal? How was the property of the crystal across its cross section? Did you make any measurement of that?
Yes, sir. It is not a crystal. It is an anti-glass disc, and for that, the homogeneity of it's measured. Since its refractive index homogeneity is of the order of 10 to power minus 3, that's why we have measured using the Schillerian method.
Okay. Okay, we move to the next.
Okay, thank you, sir.
Okay, thank you. So let's move to the second next poster. So poster is will be presented by Avantika Gautam from RRCAT. The poster number is CP0114.
Am I audible, sir?
Yes, you are audible. Please start.
Yes, sir. Good afternoon, all of you. The title of my poster is Theoretical and Experimental Studies for Development of Shield of Glass Tube CO2 Laser. So coming to the abstract part, to develop shield of glass tube CO2 lasers in India, we required mainly two things. First of all, we have to estimate the CO2 dissociation rate in the discharge so that we can design the tube with the optimum catalyst. And that suitable catalyst should be such that it can regenerate CO2 molecule after dissociation. So in this abstract paper, we have shown that a good agreement between theory and experiment was observed for decay of laser power with time. So the the power requirement, the low power requirement 50 to 150 watt for most commercial application is fulfilled by shield of glass tube laser, which are currently imported from the China. As we can see from the diagram, there is uncoated glass tube and there is a Chinese glass tube. So we have listed the element of the Chinese glass tube by the X-ray analyzer. This is our experiment laser discharge tube, and the bottom diagram is the schematic setup. So uh, to estimate the dissociation of CO2 molecules with time, we have modeled a differential equation which is used to to find the number of CO2 molecule dissociated per unit time. The equation is, in the equation, the first term is the decay rate of the CO2 molecules, where Kd is the dissociation rate, Nc is the number of CO2 molecule, Ne is the number density of electron, and C1 is the Vd by Vt. Vd is the discharge volume, Vt is the volume of the tube. And the second term representing the sidewise pumping of the CO2 molecule into the discharge tube. Going to the next slide, sir. So, for the theoretical modeling, we have used the Boltzmann code, which is used to estimate the reduced electric field in the discharge, which is governing the electron energy distribution function. And that electron energy distribution function is used to estimate the CO2 dissociation rate. And we have also included the term of pumping of CO2 molecules. So here in the table, we have shown the various parameter which is used in the discharge tube. So these are the various parameters which we have find out from the electron energy distribution function. And this is the electron energy distribution function which is which is found from the Boltzmann code. And in the left side, we have done the calculation for the diffusion time. So the diffusion time is calculated by tau d is equal to d square upon lambda d vt, where d is the diameter of the discharge tube, lambda is the mean free path, and vt is the thermal velocity. And lambda and thermal velocity is evaluated from the temperature and pressure which we are controlling. So by substituting the value of lambda and vt, we have calculated tau d as 0.02 seconds. And the dissociation, and in the table, the time for sidewise pumping in the last second row is 0.03 second coming. So these are the comparable matching of the diffusion
Time
time.
is exceeding. Please complete fast.
Yes, sir. So and the next calculation is percentage dissociation of CO2 molecules. This is N is equal to Ne Nc Kd. So going to the next slide. Basically, normally we have seen that 80% of the molecule dissociated per second in the discharge tube, but our experiment predicted that it takes almost 500 to 600 seconds to decay with the time. So we initially we have not introduced the sidewise
Please,
pumping. After
it's 4
introducing the
minutes now.
sidewise,
Please stop. Please over to judges, please.
yes sir, okay sir,
I have a question.
yes sir,
See, if you add some CO to begin with, little quantity of CO,
yes
then
sir.
your dissociation will be much less, no, in the equilibrium.
Sir, actually, CO is used. Sir, we don't require the CO. We require the CO2 for the lasing condition.
No. What I'm saying is that you are trying to build up a field of system
Yes, sir.
where you do not want that CO2 should be dissociating.
Yes, sir.
So if you add some CO already with CO2, very little quantity, then
Yes,
your
sir.
will be reached at a much lower dissociation of CO2. Should it
Yes,
not
sir.
serve your purpose?
Sir, actually, we don't want that the CO2 will dissociate it easily. Sir, because sir, after dissociation of CO2 molecule, there will be no lasing molecules of CO2.
Okay.
Hmm.
Okay. I think.
Yes, sir.
Mhm. Okay. We move to the next.
Okay, sir. Thank you, sir.
Mhm.
Okay, so next presenter is K Neetu, and the poster number is CP0115.
Hello, sir. Am I audible?
Please start presenting.
Hello, sir. Hello, sir. Am I audible?
Yes, you are audible. Please start.
Okay. My topic is study on time delay echoes in semiconductor laser with optical feedback. Semiconductor laser with optical feedback has been an intense topic of research during the past 2 decades because of its application in secure optical communication. But the autocorrelation function, which can be retrieved from the output intensity, is considered as a breach of security because it can reveal some information about the external cavity. So, in order to overcome this problem, we have to analyze the autocorrelation function and echoes of the autocorrelation function. And here we are studying the autocorrelation function for the multi-mode semiconductor laser with the optical feedback. Sir, next slide, please. So this is the system under investigation. The fraction of the light from the semiconductor laser is fed back from an external mirror. There is the external cavity. We are using the famous Lankobayashi model for the simulation. Actually, multimode extension of Lankobayashi model. These are the two weight equations which govern our study. Sir, next slide, please. So as the result, we got the output intensity, and from that we found the autocorrelation function. These are the plot for autocorrelation function. We studied the system for two cavity lengths, that is two external cavity round trip time. First one is for 0.6 nanosecond case and second one is 4 nanosecond case. And the primary peak is centered at 0 and the secondary peaks, which is called delay echoes. First primary peak is first delay echo and the second is second delay echo. So we studied actually the delay echoes should be at the external cavity round trip time, but it is found to be asymmetric and is further delayed from the expected value, that is 0.6 nanosecond case. For single mode case, the peak is little bit at the delay time, but for 3, 5 and 15, it is found to be shifting. 4 nanosecond case, it is shown as in an enlarged view. And we studied the shift from the expected value for the first delay echo, second delay echo and third delay echo as shown in the figure. And we found that as we going for the higher delay echoes, the shift is increasing. And we studied the slope also. And interestingly, for lesser cavity length, the slope is decreasing as the multimodeness increases, and for the higher cavity length, the variation is the slope is less for single mode case and is increasing as the multimodeness increases. So further studies required to understand why this cavity length changes the effect, and from here the delay echoes are asymmetric and the shift is more pronounced. Thank you, sir.
I have one question. So you need to have essentially a multi-mode laser system to characterize this, right?
Yes, sir. Actually, we are for comparison, we studied single mode case, 3 mode case, 5 mode case, and 15 mode case.
What will be the autocorrelation in case of single mode laser? Single mode means axial mode, right?
Single mode means only one mode is there.
No,
Mainly.
only one axial mode.
Yeah, yes.
Right, to single
Yes,
wavelength. Okay.
yes, single wavelength. Yes.
So what would be the autocorrelation under this condition?
Sir, that graph is shown, no, sir. Like autocorrelation function is there. Like for single mode cases also in the graph is there, sir. So shift is there with the feedback.
So how you are changing the number of modes in your
Sir,
setup?
in Lankobayashi model, the gain parameter, everything is dependent on number of mode.
You have done experiment also, right?
No, sir. Only theoretical work, sir.
Okay.
Actually, I have a question. Are you aware that chaotic semiconductor laser also can be used for secure communication?
Sir, chaos is needed. Yes, sir. Chaos is there for this secure optical communication.
So how is that different from your technique?
Actually, sir, we are giving a feedback such that chaos is there, sir. Then we are studying the time delay signature is coming like output of from the output of the chaotic output.
Okay. Okay.
Okay, sir. Thank you.
Okay, let's move to the next.
Sorry, Nita. Mr. Tatsar from BARC, the poster number is CP0117. Please start presenting, Mr. Tatsar.
Am I audible?
Yes, you are audible.
Hello. Okay. So good afternoon,
Yes,
everyone.
you can continue.
My presentation is about lasing action in CO2, nitrogen, helium gas mixture and evaluation of transition temperature. So we have earlier reported CO lasing action in 5 micron region when CO2 laser gain medium is subjected to liquid nitrogen cooled condition. These findings have established the laser emission in 5 micron region originates from CO molecules that are formed inherently in the discharge owing to dissociation of CO2 gas present in the CO2 nitrogen helium mixture. While most of the CO2 who has freezing temperature at 195 Kelvin condenses in discharge, the CO owing to its lower boiling point, that is 81 Kelvin, remains in gaseous phase, thus it forms the gain medium. In this regard, it is of interest to find the temperature regime when CO2 lasing action at 10 micron ceases and the onset of CO output in 5 micron region occurs as the gain medium is cooled. So in this presentation, we are presenting the results of our experiments where the laser power has been studied as a function of wall temperature and the cooling condition prerequisite for its operation as coherent source in the 10 micron region or 5 micron region that have been understood. So next slide, please. So in our system, as you can see in the photograph, the discharge was effected in the flowing gas mixture of CO2, nitrogen and helium at a total pressure of 10 millibar enclosed in a double jacketed quartz discharge tube whose inner diameter is 17 mm and its length is 100 centimeter. It is vacuum sealed at both ends by zinc selenide rooster plates. The outer jacket was evacuated and heat sealed, while the middle jacket is in which the coolant flowed helped to maintain the wall of the entire discharge length at desired temperature, that is at liquid nitrogen temperature. A K-type thermocouple was placed in direct contact with the outer surface of the wall of inner tube in which the discharge is struck, and it is used to study the dependence of lasing output from CO2 or CO gain medium as a function of wall temperature of the discharge gain length. For accurate temperature measurement, silver paste was used to ensure the better thermal conductivity between the tip of the thermocouple and the discharge tube wall. Next slide, please. So our experimental work is the discharge was effected in the CO2 gain medium at and the ratio of the gas medium was as CO2, helium, and nitrogen is 2:6, and it is operating at 10 millibar pressure. And this same gain medium mixture was subjected to the low temperature by way of filling liquid nitrogen in the discharge jacket. At this point, we monitor the effect of continued lowering of wall temperature of the discharge length on the CO2 and the CO2 output power, as you can see in the table. So it is obvious that the output power increases initially owing to the efficient removal of heat in the discharge until a certain low temperature below which the lasing action ceases due to the freezing of the active CO2 gain medium. So next slide, please. So as the cooling progresses, the gain medium becomes less and less conductive.
Please complete fast.
For CO2 laser operation, while favoring building up of gain for CO lasing. The output power was monitored continuously to see if the lasing in the 5 micron region had begun by placing the sapphire crystal in front of the laser beam that completely cuts off the CO2 power and allows only 5 micron output. So it has been observed for the given cavity configuration that no lasing action takes place in the range of temperature of
Please
minus
stop. It's
38 degrees centigrade to
over
minus
to judges,
70
please.
degrees centigrade, either in 5 micron or 10 micron. Thank you.
So that CO lasing in the CO2 laser, it is from where the CO is coming there?
Yeah, actually, sir, it is because of dissociation of CO2, sir.
Dissociation
The
of
CO is formed inherently in the discharge, sir. That CO only takes place in the lasing action.
Okay. So there is no external CO gas is required.
Yeah, this is the main importance of this system, sir. We are avoiding the CO gas cylinder, which is very toxic.
And what about that efficiency and all these things in this case?
Efficiency is most likely in free running conditions, sir, it is good as CO2 means around 10%. But in cavity operational means cavity config, if you want to use grating and all, the efficiency will drastically decrease in that case.
And
otherwise, efficiency is okay, sir.
And what about that? The system is cooling, the diffusion cooling type of operation.
Yeah.
Then
Yes, sir.
how it is governing there then? Because the wall temperature may be very less.
Yeah, but CO, for CO it is beneficial, sir. CO laser efficiently operates at liquid nitrogen cool temperature only.
Okay.
10 to 15 minutes.
So next speaker would be Mr. Bhuvnesh from RRCAT. The poster number is CP01 and 18.
Hello, good afternoon. Sorry.
Please keep within 3 minutes, please.
Okay, sir. So I will be presenting on development of a 5 watt linearly polarized CW output from all fiber amplifier at 1064 nanometer with the spectral width less than 0.2 nanometer. We are pursuing this activity because a laser system with more than 5 watt polarized output at 1064 nanometer with the specified line width is required at RRCAT in some lab. Obtaining such a high power, that is more than 5 watt, and spectral width less than 0.2 nanometer is difficult from directly from oscillator. So amplification of a low power seed source is preferred. Now this amplifier can be based on this conventional solid state amplifier or fiber based amplifier. Now we are preferring this fiber based amplifier because fiber amplifier have many advantages over conventional solid state counterparts. Now, the main problem which are associated with the fiber amplifier are generation of amplified spontaneous emission, that is ASE, SBS, heating, and signal loss at the splice point. So before the actual design, we have taken proper simulations to minimize these effects. Next slide, please. Yes, this is our experimental setup. Now we have a seed source and a double clad based amplifier. Now this amplifier is pumped in clad by a multi-mode pump diode delivering around 30 watt power, and this output from the collimator is polarized using a polarizer, and the other one part of the polarization we have measured, and the other is blocked by a beam blocker. Next, please. Now, here I will summarize the result obtained from the amplifier. Now, it can be seen from figure 1 that amplifier output increases with increase in the pump power. And with corresponding to around 17 watt pump power, we got around 5.2, more than 7 watt output, which correspond to a 40% conversion efficiency. And this 7 watt is polarized. Now, to check the stability of amplified output, we run the amplifier many times, and figure 2 show a typical result. Now, it can be seen from figure 2 that the output power is stable and fluctuations are within 5%, which are acceptable. And to measure the spectral width, we characterize the output from amplifier by using a spectrum analyzer, and we measure the line width, which come out to be less than 0.2 nanometer. So we developed a all fiber amplifier setup using YB doped gain fiber for amplification of fiber coupled sheet source from a level of 200 milliwatt to a level of 5 watt, actually 7 watt, and it is polarized and its line width is less than 0.2 nanometer, which is our aim. Thank you.
How did you,
Please. Hello?
How did you ensure that the line width was within 0.2 nanometer?
Hello? Hello?
How did you ensure that the line width is within 0.2 nanometer?
Okay, so we measured the line width of seed source, which comes out around 0.15 nanometer. Okay, then after each amplification stage and after amplifier, we measured the line width and it comes out around 0.15 itself. By using spectrum analyzer, we measured it and we saw that line width is well within the specified limit.
Okay.
Yes.
Okay, we move to the next, please.
Okay, so next we will move to poster sessions with the heading of ultra-fast laser and its applications. So, Mr. Jitendranath Acharya from IIT Delhi, and his poster number is CP0601.
Yes, sir.
Mr. Jitendra, please start.
Yes, sir. Am I audible, sir?
Yes.
Yeah. Good afternoon, everyone. I am Jitendranath Acharya, working under the supervision of Professor G. Vijay Prakash, Department of Physics, IIT Delhi. This work is done under the mentorship of Professor D. Narayan Rao, Professor G. Ramesh Babu, Professor my supervisor, Professor G. Vijay Prakash. Today, I am going to present enhanced optical nonlinearities in metal dielectric one-dimensional photonic crystals. Move on, please. So here I will actually show the use of ultrafast laser and hyper laser in the domain of ultrafast and nonlinear optics. So here the photonic crystals. What is photonic crystals? Photonic crystals are the novel optical media where refractive index shows periodic modulation in order of optical wavelength. It could be artificial or natural. These two scientists, Aplanovich and Professor John, who first showed the control of spontaneous emission and the local field enhancement in 3D photonic crystals. This is one typical example of all dielectric distributed drag reflector, one example of a 1D photonic crystal left side, which shows it reflection and transmission spectrum in black and red region, where this region, completely blank region, is called the photonic band gap, where photon propagation inside this structure is strictly prohibited, like semiconductor. And if we replace this all dielectric photonic structures by metal one, we can access the ultra fast and high optical nonlinearity of metal. So we will move to the metal dielectric photonic structures, but the problem is the huge loss of the metal. Next slide, please. So in this study, we fabricated three sort of metal dielectric structures: 4 bilayer AgSiO2. Sorry, previous one, please. 4 bilayer structures, SiO2, 1 bilayer, and single edge film. So we'll focus on the third order and higher order optical nonlinearity and ultrafast dynamics. So for study the ultrafast dynamics, we implemented femtosecond pump probe spectroscopy, where a pump beam divided into two parts, acting as a pump beam which excites the sample, and the other part of the beam is focused on a calcium fluoride crystal to generate a broadband supercontinuum to monitor the pump-induced modification inside the structure. And this is the femtosecond G-scan technique, where a Gaussian laser is focused on the sample, and the transmission through the sample is is recorded in each G position, and the nonlinear absorption, nonlinear refraction is recorded. Next slide, please. So this is the typical, this is the reflection transmission spectrum of the AgSiO2 4 wireless structures, where photonic band gap is between 400 to 600 nanometer. This is called the photonic mini bands, where there is a transmissive region in the visible and NIR region. Though we have used a large amount of metal, but we still have transparency in the visible region. So we can access the large and ultra fast nonlinearity of the metal. And this is the photonic band gap simulated one. And this is the experimental nonlinear jet scan technique with varying laser intensity, and we can see the strong 2-photon and multi-photon absorption behavior at 725 nanometer, one photonic miniband region. And this is due to the Ag intrinsic nonlinearity is getting manifold enhanced because of the Ag SiO2 Ag configuration, Fabry-Pérot configuration. Here it is acting as a coupled Fabry-Pérot resonator. And this is the optical limiting behavior, where we can use it as a femtosecond hyper laser operation sensor protector. And this is the ultrafast dynamics, where we can monitor electron phonon interaction in this metal electric system, and we can utilize in this this is as a femtosecond hyper laser operation. And also we observe the femtosecond supercontinuum generation by pumping this 800 nanometer pulse, and we can get a broadband supercontinuum generation. So this is a stable supercontinuum source and also a stable solid state nonlinear media. Next slide, please. Thank you. These are the references and these are the acknowledgements.
Over to judges, please.
I have one question.
Yes,
so it is basically Fabry-Pérot cavity.
Yes, sir. Yes, sir. Multiple Fabry-Pérot cavity acting as a coupled Fabry-Pérot resonators.
So why you are saying it is a photonic structure?
Yeah, photonic structure, because this is a photonic crystal, because in a crystal there is a specific lattice constant, lattice parameter, which follows a lattice parameter at distance atoms are arranged. Here the layer, here the one-dimensional photonic crystal, because this layer are arranged in alternative arrangement of two different refractive index, N1 and N2 layer. And the thickness is in order of lambda by 4. That's why it is called the photonic crystal.
That you have made the layers fine, but
Yes,
your that material which is actually showing that enhanced nonlinearity,
yes, sir.
that is sandwich between these two set of layers, right?
No, the total first structure is alternative 4 bilayer structures, AgSiO2, AgSiO2, total 8 layer of AgSiO2.
Okay.
And the second one is AgSiO2 1 bilayer structure, and third one is single Ag film. Because of the short time, I just showed the one structure.
Okay. So this nonlinearity is getting enhanced due to this periodic positioning of your silver silicon dioxide layer.
Yeah, because of the two-side Ag, and in between there is SiO2, and huge photon flux are getting confined within the SiO2 layer, which manifold enhance the Ag intrinsic nonlinearity. By this photon confinement, huge photon confinement. If we see this simulation, we can show that is.
So you measured the chi3 of the arrangement.
Yes, sir.
Have you also observed that measured the 2-photon coefficient? Or
Yes, all I have measured actually in that instance. Yes, sir.
Okay.
It is almost 10 to the power 5 orders of magnitude higher as compared to one layer and single Ag film.
Okay.
Yes, sir.
Thank you.
Thank you, sir.
Okay, so next presenter is Dipanjan Banerjee, and the poster number is CP0602.
Good afternoon.
Dipanjan, please
Am I audible?
start.
Good afternoon, sir. Am I audible?
Yes, you are audible. Please start.
I am Dipanjan Banerjee from University of Hyderabad. I'll be presenting in this National Laser Symposium 30 about quasi-periodic silver nanostructures achieved with ultra-fast basal beam ablation for real-time detection of various hazardous materials. Next slide, please. So this is the experimental setup of laser ablation using a Hexicon prism lens, which is the first time report to the best of our knowledge on any plasmonic material. Here you can see we have done extensive energy dependent studies to fabricate basal beam induced silver nanostructures to achieve their various applications. So the usage of basal beam has its own advantages, like its invariance of intensity through the propagation up to a certain distance. Along with, if it faces any obstacle, it can revive its own profile on its own due to self-interfering properties. So we have used a picosecond laser, 10 Hz, 30 picosecond, 1064. The significance of using 1064 nanometer is to achieve the multiphoton absorption, to fabricate far better nanostructures. So here you can see the profile of the basal beam, which is shown in the diagram. This is the profile imprint on the silver substrate after incidence of 5 seconds. That means 50 pulse of picosecond laser. Next slide, please. Next slide, please. Yeah. So after the fabrication of picosecond laser induced basal beam induced rigorous nanostructures, so these topographical characterizations were thoroughly carried out. First with FESM and after that AFM to get the nanoscale insight of their formation of nanostructures as well as their nanoscale surface roughness. On the left side, you can see different magnification of images, which is giving the clear insight that the fabrication of finger-like nanostructures. And after that, you can see, no, the previous slide, please. Yeah. And after that, you can see the EDAX spectra, which is extensively providing the information of the occurring of no oxidation. And on the right side, you can see the AFM images, which is giving clear insight to the nanoscale roughness of the fabricated nanostructure surface, which is a very important parameter to provide hotspots for surface enhanced Raman scattering signal. Next slide, please. So after this, from the fundamental physics point of view, the basal beam ablation has been quite interesting as the report is for the first time on any plasmonic material like silver. After that, these fabricated structures have huge application from the real-time application point of view, as they were utilized as ACRS substrates to sense various hazardous materials, such as real-time explosive, which is picric acid. You can see in the left side that 6 new molecules have been detected up to 50 picomolar regime with the portable Raman spectrometer, which is quite real-time in the real-time domain, which is quite interesting. And then the right side, you can see that the micro-Raman mapping data, which has been provided to to give you the picture of the plasmonic response of much lower resolution of these nanostructures.
The time is crossing. Please finish.
Yeah, I'm done. Next slide, please. So this is the conclusion, which says that this is the first time report on silver with the basal beam, which is providing a versatile, recyclable and reproducible silver nanostructures. And here are the acknowledgements. Thank you.
Okay. I have one question.
Yes.
So what is the basal beam is helping in that surface mod? You're basically doing the surface modification using basal beam, right?
Yes, yes. So in case of Gaussian beam, we all know that it is well exploited. It has a full width half plate ceiling and it has a Gaussian profile. But in case of basal beam, the interesting part is I have shown in my second slide. It has a central lobe where it is depositing the maximum energy. Along the rest of the energy is deposited in terms of concentric rings, which creates interference when you do a raster scan. It's kind of interference of two basal beam induced ablation waves propagating on the substrate.
No, whether the surface being structured as the profile of the basal beam, or you are scanning over the sample.
Yes, the surface is being modified according to the profile of the basal beam, and
are you scanning across the surface?
Yes, we are scanning across the surface, and we have scanned at a single spot also to give the insight of the single spot profile imprint as well as the imprint when it is scanned through the substrate of the surface of the substrate.
Fine. And what is the energy of the picosecond pulses?
The energy is we have studied at four different energies from 12 millijoule pulse energy to 24 millijoule pulse energy. Extensive energy dependent study has been done, and this has been communicated actually. This is up to the best of our knowledge. This is the first time report of basal interaction, ultrafast basal interaction with silver.
Okay.
Did you compare your results with and without Axicon?
Yes, sir. We have compared the results with Gaussian beam also, and that means with some other lens. and with Hexagon we have compared, these results are at least like 3 order better in terms of surface enhanced thermal scattering enhancement. So that means in terms of the plasmonic response which is coming out of the finger-like structures, finger-like nanostructures which are fabricated, which are so rich in plasmonic band in terms of, we can say, so it is giving so high response that I can say you in terms of enhancement factor, it has given 10 per 8 to 10 per 9 enhancement factor, and in terms of detection limit, it has an LOD of I think 30 picomolar for an explosive, right? So which is fundamentally very interesting, as well as from an application point of view in real-time world, like any terrorist activity or such thing, such activities. So it is in that point of view also it's quite interesting.
Okay.
Thank you.
So let's move to next poster. CFB. The poster number is CP0603.
Amount of noise is
here.
Hello, shall I start? Hello.
Please start, FB.
Okay, okay. Femtosecond laser induced heat propagation and damage threshold analysis of gold chromium 2-layer film. Next slide, please. Hello. By this work, we have aimed to understand the non-equilibrium heat propagation through electron-phonon coupling in a femtosecond laser irradiation on metal. For that, we develop a code based on two-temperature model and analyze the damage threshold and explore the enhancement of damage threshold of metallic films like gold and gold chromium double layer.
Speak a little
hello?
louder.
Hello, yes. The knowledge of damage threshold is very important in ultra-fast laser systems. Hello. Because one of the limitation of femtosecond development of high power femtosecond laser system is the peak power handling capability of their optical components. We also studied the effect of different thermophysical models on predicting damage threshold. Please, next slide. Mathematical formulation. We use the two-temperature model for theoretical understanding of femtosecond laser matter interaction. Two-temperature model consists of two coupled partial differential equation, one for electron and other for lattice, coupled by electron-phonon coupling term. We solve this equation numerically by developing a Python-based code TTM-FS. For our work, we used the two models. For this model 1 and model 2, in those cases, we use different modeling of electron lattice coupling strength and thermal conductivity of electron. Other variables are kept as same. We also validated our code with the published results. Next slide, please. Please. Result. Before that, the damage threshold is defined as the minimum fluence that causes the melting of the film. The top two figures shows the electron and lattice temperature profiles of laser irradiated surface at a particular fluence 2800 joules per meter square. The dotted lines correspond to the model 1 and solid lines correspond to the model 2. From this plot, we can understand that the presence of substrate as chromium reduce the surface temperature. The CN line shows the reduction of the surface temperature. That point in the direction of enhancement of damage threshold. The below two figures represent the damage threshold values with respect to model 1 and model 2. From that figure, we can also understand the two models give qualitatively and quantitatively different damage threshold prediction. That means in prediction of damage threshold, this thermophysical modeling play a crucial role. Also, we got maximum enhancement of 6% in 100 nanometer total thickness and 9% for 200 nanometer total thickness. That means the damage threshold of double layer film depends on the total thickness values. Okay, thank you.
Over to judges.
I have one question. What is the,
okay, sir.
You said it is for the femtosecond. So what is the range of femtosecond value for which this model will be valid?
This two temperature model main criteria is that if the pulse duration of the laser is lower than the electron lattice equilibration time, it is valid. Uh, Mostly it is generally valid all range, but we can use one temperature model if the pulse duration is higher than the electron lattice equilibration time.
What is what is the typical value of this? Means
here electron phonon.
When we say femtosecond, it ranges from 3 femtosecond to 600, 700 femtosecond. That is also we refer to as femtosecond pulses, right?
Okay.
So,
because normally electron lattice equilibration time in picosecond range, 10 or 100 picosecond time. Below that we can call as femtosecond laser.
Okay.
Because our work we use 100 femtosecond laser. That means
so
0.1 picosecond.
So the model you have used, that would be valid for pulses below 1 picosecond. That is what you are saying, right?
Oh, but it is generally valid for other cases also. But there is no need of this two temperature model in nanosecond pulse duration lasers.
Okay, but your title specifically says it is femtosecond, right?
Yes. My work is now because I use femtosecond lasers.
Okay. So have you validated this with experiment, or it is only theoretical?
Only theoretical.
Okay.
Can you tell the physical reason why ceramic substrate reduces the surface temperature?
Mainly this is that. Hello.
Yes.
This is not ceramic. This is metallic substrate, chromium.
Oh, chromium. Sorry, chromium substrate.
Metallic. That is mainly because of the electron phonon coupling term. Because it easily absorbs energy from the laser incident layer. This chromium second substrate layer.
So electron phonon interaction is enhanced when chromium substrate is used.
Yes. One criteria is that.
Have you tried some dielectric type of things?
Now we only tried these things. Recently we started this study.
For dielectric materials?
No. Now we only study the metallic substrate.
Okay. Okay, thank you.
Okay, thank you.
Okay. So next presenter is Bhavna Rane from IIT Roper, and poster number is CP0604. Please start.
Hello, am I audible, sir?
Yes, you are audible. Please start.
Okay, good afternoon to everybody. This is Bhavna Rana from IIT Roper. The topic of my presentation is producing liquid microjets using picosecond laser pulse excitation. So the motivation includes basically the needle waste, which is associated with the medical industry. According to WHO reports, 16 billion injections are administered every year, and owing to their improper disposal, they are basically leading to the disease spread worldwide. So in order to combat this particular situation, various needle-free jet injection systems have been introduced and being improvised with time. The conventional systems includes compressed gas springs, and there is piezoelectric transducers. But recently, these introduction of lasers in this field of needle-free injection systems has revolutionized the field. Next slide, please. Using lasers, let me tell you, for example, we consider the top left figure, where if we used to impinge the laser on a microcapillary, then with the absorbance of laser energy, there is a formation of bubble or cavity in the medium, and due to the pressure difference at the air liquid interface, it leads to the generation of microjets. These microjets are very focused, very fine in diameter, and of very high speeds, and hence they overcome the limitations of clogging the nozzles in the conventional needle-free injection systems. So that's why these laser-based injection systems could be very helpful in the development of this medical industry. So this is the experimental setup using this NDR picosecond laser system, which we are using at IIT Roper for the evaluation of these needle-free injection systems using these microjet formations. And the right-hand figure is the side view of the microcapillary, where which is intended to show various parameters which are crucial for the generation of these microjets, like shape of the meniscus, the laser hitting position, the capillary diameter. Next slide, please. So in the result and discussion section, we have successfully demonstrated that how the variation of laser absorbance can tune the jet formation and jet speed, for which we have utilized this rhodamine 6G sample, which have shown this significant concentration dependent variation in the absorbance around 528, 530, 532 nanometer, and which we have further utilized for the formation of jets as shown in the middle panel. And here we have also tried to provide a mathematical correlation between the laser absorbance and hence the jet speed. Basically, the applicability of this work is very helpful in order to achieve a broader prospect of this desired penetration depth targeted drug delivery systems. Because if you see the drugs which we used to inject in the human body, they used to consist of various kinds of surfactants and salts, which may alter the energy absorbance of the laser which we are going to use for the jet formation. So if the presence of this salt alter the laser absorbance, the jet speed will vary and hence one will miss the target. So in order to achieve the targeted drug deliveries, one need to take into consideration this laser absorbance parameter. That is what we are trying to do here. Thank you.
This jet you are making with the help of a NDR laser?
Yes, sir.
So that a jet, just suppose you are telling that you are using a rhodamine 6G dye.
Yes, sir.
You have used that some concentration of the rhodamine 6G dye.
Yes, sir.
Because of the rhodamine 6G dye, the rhodamine 6G has a very good absorption in that 532 nanometer.
Yes, sir.
So then what will happen? The total intensity will also, pump intensity will also reduce, the NDR will reduce.
Sir, in the NDR laser system, what we have done, we have used the NDR laser system. What we have is 1064. So that we have further, if we move to the second slide of the presentation, where you can see that this 1064 is further used in the second harmonic unit in order to generate the 532.
Correct.
So ultimately that 532 we are impinging on the microcapillary, and then further phenomena of laser absorbance and ultimately that bubble formation and that jet formation is taking place. So our motive is to make people understand that this laser absorbance, for example, if you change the concentration of the rhodamine sample, so obviously the laser absorbance will change. And keeping the pulse energy same, for example, if I'm working with 200 microjoule of 532 nanometer, let's say, so keeping the same laser energy but with different rhodamine samples, that is different absorbance of lasers, I'm getting lasers, these jet speeds of 40 meter per second in comparison to 8 meter per second.
So you are reducing the power of your laser.
No, fixed laser energy fixed.
Laser energy is fixed, but when you are passing it through the rhodamine 6G sample, the rhodamine 6G itself will absorb that 532. Because it is a very good absorption at a 532.
Yes, because of that, we are observing this increment in the jet speed, no?
I couldn't get you. Okay.
Sir, the concern was that this 532 absorbance will increase if you raise the rhodamine concentration, right?
Definitely, but in that sample.
In
that sample, but how will it form the jet? For a jet formation, you have to drill a hole.
No, sir. In order to form the jet, definitely you need, sir, in case of laser induced jet formation, the phenomena is the formation of a cavity inside the microcapillary, and the cavity is dependent upon the laser absorbance.
Okay.
So
hello, I have a question.
Move to next poster.
You
so
mentioned
next presenter is Resma Biram from University of Hyderabad, and the poster number is CP0606.
Yes, yes. Am I audible?
Miss Resma,
Yes,
you
I'm
can
there.
start now.
Okay. So, good evening, I'm Reshma Biram. I'm going to present my work on web-like silicon nanostructures fabricated via femtosecond laser ablation and its application in surface-enhanced Raman spectroscopy. This work is done under the supervision of Professor Soma Venugopal Rao, Akram, University of Hyderabad. So, I'll first briefly talk about what is femtosecond laser ablation and motivation for our experiment, and then I'll present our results on laser ablation of silicon and effects of different laser parameters. I'll briefly discuss the mechanism of formation of these web-like structures, and then I'll present the application of these structures in surface-enhanced Raman spectroscopy. Next slide. Next slide, please. So, femtosecond laser ablation is a tool for precise fabrication of micro and nanostructures on various materials. But usually, ablation experiments are performed with an amplified laser system, which are usually expensive. So here we have used a simple femtosecond laser oscillator system with a pulse duration of 140 femtoseconds and repetition rate 80 megahertz. For our experimental setup to achieve nanostructures on silicon. So this is the schematic of our experimental setup. So the laser is focused on the silicon sample using a long working distance objective, and the silicon is translated using XY stages to make line and square patterns. So these structures were characterized using FSM. So typically in a femtosecond laser ablation experiment, different laser parameters like wavelength, pulse duration, time, beam profile of the laser affect the results. So we wanted to see how these parameters affect our silicon structures. So we started studying the effects of number of pulses per spot. We changed the number of pulses per spot by changing the scan speed of the laser. We started with two extreme scan speeds of 0.05 mm per second and 2 mm per second. And we also studied a couple of intermediate scan speeds of 0.1 mm per second and 1.5 mm per second. So as you can see, in all these cases, you have the silicon nanoparticles aggregating into nanofibers, which further self-assembled into web-like structures. But in the cases of lower scan speed, the density of these nanofibers is higher than that of higher scan speed, and also the size of the nanoparticles within these web-like structures is smaller for the case of lower scan speed relative to higher scan speed. So we wanted to see what fluence can do to these silicon nanostructures. So we changed the laser fluence by changing the working objective from 100x to from 50x to 100x, and we studied structures at same scan speed. So this case, the silicon nanoparticles interestingly aggregated into clusters rather than web-like structures. In comparison, you see an image of 50x objective with same laser power and same scan speed. So we wanted to see if we can go back to these web-like structures by changing the laser fluence for 100x objective as well. So we decrease the laser fluence for the 100x case, and as you can see in figure 4, we got back to the web-like nanostructures for 100x objective as well. So we believe that there's a threshold fluence for the formation of these web-like structures. So we have used these silicon web-like structures for surface-enhanced Raman spectroscopy. Surface-enhanced Raman spectroscopy is an improved Raman spectroscopic technique that uses localized surface
Try to complete fast.
Yes, sir. One more minute. Localized surface plasmon resonance in metal nanostructures for signal enhancement. So we have taken laser structured silicon with scan speed of 1.5 mm per second for our search studies. So we have made square patterns, as you can see in the image for our search studies, because these have proven to have an advantage in our previous studies. The sample to give them plasmonic nature, the sample was coated with gold by thermal evaporation method. So we have chosen methylene blue as the probe molecule, and in figure 6 you see images of our search spectra. As you can see, the laser ablated silicon clearly has an advantage over plain silicon. The signal is enhanced in the case of search. We have studied methylene blue at different concentration, and we could detect concentration as low as 1 micromolar. And the reproducibility for the substrate is also 18%, which indicates good reproducibility and practical use. Thank you.
Over to judges, please.
I have one question. Whether this you are making
Okay, sorry, can you please go to the next slide? I was in the next slide.
Your time is over. It's up to 5 minutes.
Yes, yes. No, no. This slide is already presented. The slide was not changed. My
Okay,
presentation is over.
Judges, please proceed.
Yeah. So by laser texturing using
Yes.
femtosecond pulses, you are enhancing the Raman signals, right?
Yes, yes.
So, whether it is making the surface as a super hydrophobic type of thing, so that the sample concentration keep on increasing there, localized.
So here we haven't studied hydrophobicity, but in general, laser structure materials exhibit higher hydrophobicity than normal structures.
Then how it is enhancing the Raman signal means a nanomolar level you could
Yes,
detect,
yes,
right?
yes.
So
We detected micromolar. Two possible reasons is silicon will give a chemical enhancement because by charge transfer mechanisms. That is chemical enhancement is one reason. Our order of enhancement is also 10 power 3, which is in the range of chemical enhancement. So we suspect chemical enhancement, and also because these nanofibers offer higher what
no,
absorption
if the
area
substrate
and
has the role in the substrate has the role for the Raman, then the sample is actually influenced by the substrate, isn't it? Suppose if you want to measure the Raman of any Raman signal of any sample and put on this substrate, so it will be influenced by that.
yes, sir. In general, you have substrate effects in Raman surface enhanced Raman spectroscopy. So chemical enhancement is also a contributor to surface enhanced Raman spectroscopy, but it's relatively smaller than electromagnetic enhancement.
Okay. Okay, fine. So you mean to say that structure is helping in that? That is
Yes,
what you
sir.
are saying.
Yes, sir.
Oh,
And also this will offer higher absorption area because you have nanofibers, so there's more absorption area
yeah.
for the analytic.
My point is that a similar texturing can be used with can be obtained with nanosecond pulses also. Why you need femtosecond for that?
We have worked with the nanosecond pulses, but we got random stacking instead of these web-like structures. So these web-like
Okay.
structures are very unique for femtosecond laser.
Fine. Fine. Very good. Thank you.
Thank you.
So next presenter is Mr. Pradeep Kumar Gupta from RRCAT, and the poster number is CP0607. Mr. Pradeep, please present.
Sir, I am audible. Hello.
Yes, you are audible.
Yeah. So this is generation of vector dark light pulses from fiber laser mode locked by nonlinear multimode interference. So multimode interference in optical fibers have been used for sensors like displacement sensor, current sensors, temperature sensors, magnetic field sensors, etc. And for mode field adapters for designing a wavelength tunable laser source and high power fiber lasers with good beam quality. Recently, multimode interference as saturable observer based on Kerr-induced nonlinear effect has generated a lot of research interest. Here, we present mode locking operation in fiber laser using nonlinear multimode interference based saturable observer. So let us see what is multimode interference in optical fiber. So to observe multimode interference in optical fiber, we splice a multimode fiber between two single mode fibers. So when light is launched into multimode fiber from a single mode fiber, several higher order modes are excited into the multimode fiber. These excited modes propagates into the multimode fiber with their respective propagation constants. Now, along certain locations, when these propagating modes are in phase, they create a constructive interference pattern that create image of the input field profile like shown here. Now, this occurs repeatedly along the multimode fiber. So, the distance between these self images is known as self-imaging interval. Now, if we splice another single mode fiber exactly at the location of this self image, nearly whole of the light is transmitted to the single mode fiber. So this is the case with a monochromatic light source. If the light source is broadband, so due to mismatch of these propagation constants along this self-imaging location. So these wavelengths are actually separated. So after splicing this single mode fiber at this location, only a band of wavelengths are transmitted to this. So this MMI structure acts like a band pass filter. So this is the case of multi-mode interference in linear region. Please go backward. Yeah. So since in the fiber lasers, light is concentrated into a very small core diameter of fiber, so we cannot ignore the nonlinearity. So we have calculated the intensity dependent transmission. So this MMI structure for different operating wavelength. So here for design wavelength, the self-imaging occurs exactly at the splice plane. So initially light is transmitted completely, but when the light intensity is increased, this self-image location moves away from the splice plane and the transmission decreases. So for this operating wavelength, this structure acts as a reverse saturable observer. So for some different operating wavelength, say the operating wavelength is larger than the design wavelength. So initially this self-image occurs at this left side of this splice plane and the transmission is lower. Now with increase in intensity, this self-image location, it moves toward the splice plane and the transmission through this structure increases. So in this way, for this wavelength, so it acts like a saturable observer. So when we insert such MMI structure into a fiber laser, and we insert some filter, so its combination acts like a saturable observer. So please go to next slide.
Try to complete fast.
Yeah. So here I have shown the laser setup. This is the gain fiber. It is pumped through a laser diode. And we have used two MMI structure, MMI 1 and MMI 2. So this MMI 1 is acting as a band pass filter. Here I have put a polarization controller. It's tuned the center wavelength of the band pass filter, and this is the MMI 2. It's as a saturable observer. So initially at low pump power, when the polarization control knobs are loosened, so the laser setup works in CW mode, as shown here. Now as we increase the pump power and we tighten this polarization controller, so we get a train of bright pulses onto the oscilloscope. Please go to the next slide. Next slide, please.
Please complete fast.
Yeah. Now, with further increase in stress by rotating the polarization knob, we get dark white pulse pairs as shown here. So this dark white pulse pair, it has three components basically. One bright.
Hello, Pradeep.
These dark bright pulses, they have vector nature. So their spectral profile are also different. So we have produced these dark bright pulses in MMI based mode log fiber laser setup. Thank you.
If you are splicing a single mode fiber with a multi-mode fiber in between.
Yes,
yeah, what is the core diameter for this multi-mode fiber and a single mode fiber?
We have used 50 micron multi-mode fiber and 6 micron single mode fiber.
So what is you have to use some certain length of this multi-mode fiber to develop that modes?
We have to pre-calculate these multi-mode fiber. Basically, they are integral multiple of self-imaging interval here. It is around 5 centimeter.
Okay.
Yes, sir.
So next presenter is Mr. Pal from RRCAT. The poster number is CP0605.
Am I audible? I will share my presentation, just a minute. Just a minute. I have to share. Just a minute. Yeah, is it visible? Hello.
Yes, it's visible. Please go ahead.
Okay, thank you. Okay, good afternoon, everyone. Myself, Nitish Pal. I am a PhD student at RRCAT Indore. The topic of my presentation is noise like from all version Y video all fiber oscillator mode log by semiconductor saturable absorber. So Here you can see, so first, as the title suggests, this is the presentation is about the noise-like pulses. So what is noise-like pulses? So, you can see at the left end, so this is the structure of a noise-like pulses. This is a branch of random temporal fine structure within a wide envelope, which repeats at the cavity round trip time. So it is quite different from the normal or the conventional mode-lock pulses. Here you can see this type of noise-like structures. So these are the basically simulated structure. In real time, you can't see all this kind of fine structure in a real-time experiment. If you want to see these kind of things, so very high, large bandwidth oscilloscopes are required. But then how to characterize this kind of noise-like pulses? Then we have to we have to depend on the autocorrelation traces. So this is the intensity autocorrelation trace of a noise-like pulses. You can see a spike riding on a broad spectrum. The typical order of these spikes are of the order of some 100 of femtosecond, whereas this broad spectral are basically of the order of 100 of picosecond. So this kind of autocorrelation traces are very different from this conventional autocorrelation of a mode-lock pulse. So to generate this kind of noise-like pulses, we have done some simulation to go further in the experimental stages. So first, when we did this simulation, we take this kind of prototype oscillator setup. So this is the setup you can see. So this is basically a gain guided setup, so where no band pass filter is used. In general, in an all normal dispersion fiber laser, we generally use a band pass filter, but here no such band pass filter is used. So in that sense, it's a kind of a unique oscillator. So now what we have done, so we model this oscillator with this Greensburg-Landau equation. Here U is the field envelope which is circulated inside the cavity, and this is the gain term, and this is the bandwidth, finite bandwidth of the gain medium, which is acted as a filter in this case. And this is the saturable absorber term, which we have used in this case is a semiconductor saturable absorber. Now this what we have done, that we change this cavity length and try to find out the range of parameter space where we can find where we can find a noise like
3
pulses.
minutes
So
is
as you
over.
can see that, okay, sir, just a 1 minute. So as you can see, we increase the cavity length, we get so at the end of this length we get a noise like pulses.
Go to the
And here
go
you
to the
can
conclusion part. Experiment and
okay.
result.
Oh, so we have then used these experimental results to get this kind of noise like pulses. Thank you.
Okay, I have a question. You
Yes.
have used a unidirectional, that is traveling wave cavity ring laser. Now,
Yes, sir.
a traveling wave cavity ring laser will support operation only on a single longitudinal mode, right?
Not necessarily, sir. I mean, if it is single longitudinal
Why
mode, then
in a traveling wave cavity there cannot be any spatial hole widening?
no, sir. If there is not more than one longitudinal mode, the mode locking process will not initiate it.
No, so what I'm saying, that why in a traveling wave cavity laser, it should always live on single mode. So how do you get mode lock pulse in the first place?
Sir,
Oh,
hello.
yes.
Sir, if there is not a more than one, I mean, few longitudinal modes,
See,
there would be,
yours is a homogeneously broadened gain, right?
yes. I
And
mean,
in a homogeneously broadened laser, if there is no spatial hole widening, which is the case with traveling wave cavity, you cannot get more than one mode. That is the basic laser physics says that.
yeah,
So,
that's true. But but the thing is that If there is no
Nitish,
more than one single.
are you sure that your gain medium is homogeneously broadened?
No, sir.
What is the gain medium used here?
Why of gain fiber?
Gain fiber is made of what?
Fiber of made of silica.
Silica glass, right?
Silica glass and doped with YB. Yes.
So what is the nature of glass?
It's inhomogeneous. No. It is inhomogeneous. That was I was telling, sir.
Okay then. How did you get traveling wave cavity? That is unidirectional emission.
Sir, this is isolator makes it unidirectional.
Oh, so you used an isolator. Okay. So we go to the next.
So our next presenter is Sugandha Siroi from IIT Madras, and the poster number is CP0608.
Sir, am I
Please
audible?
Yes, you are audible. Please go ahead.
Okay. Good afternoon, everyone. My name is Sugandha Siroi, and I am currently pursuing my PhD at IIT Madras. Today, I will talk about my work on laser-induced optical and thermal effects due to high repetition rate pulse laser. When an ultrafast pulse interacts with a nonlinear material, then due to the cell phase modulation effect, the phase of the beam changes. However, if we use a high repetition rate pulse laser, then apart from the nonlinear optical effect, thermal effects also come into play, and they change the refractive index of the material as shown in the slide, which also leads to change in the phase of the beam. Now, the total phase change has an optical as well as a thermal contribution. The thermal contribution depends on dN by dt, the thermo-optic coefficient, and the change in the temperature of the material. Next slide. The change in the temperature of the material is numerically simulated by using the finite difference simulation method. As seen in the first figure, for the pulse duration tau p, the temperature of the material rises and then it decreases before the arrival of the next pulse. The build-up of temperature in the material depends on the characteristic rise and relaxation time of the medium. As seen in the last figure, the spatial cell phase modulation effect is experimentally investigated by looking at the far field diffraction pattern of a high intensity beam when it passes through the sample. This diffraction pattern is the combination of the optical as well as thermal nonlinear effect. Next slide, please. The thermal effects depend on various pulse parameters. First and foremost is the repetition rate, then the pulse duration, and the energy of the pulse. If we look at the first figure, that is for 10 Hz, that is low repetition rate, then the pulse to pulse duration is quite less than the characteristic relaxation time of our material, which was sulfuric acid, and the characteristic relaxation time was of the order of 0.12 millisecond. Hence, the temperature of the material dissipates before the arrival of the next pulse, and the temperature does not build up over time. But if we look at the second figure and we go for higher repetition rate, that is 100 of kilohertz to megahertz, then with each pulse, the temperature builds up in the material and eventually reaches a steady state temperature. Higher the repetition rate, the higher is the steady state temperature. If we go for third figure, we see that longer is the pulse duration, the higher is the steady state temperature. In the table given here, we have summarized the steady state temperature for various pulse energy, pulse duration, as well as the repetition rate. It can be easily seen that the thermal effects are more prominent for high pulse energy. As the Gaussian beam has a transverse intensity profile, the far field diffraction pattern is dark and bright circular concentric rings. These diffraction pattern can be used to find the various nonlinear parameters like the nonlinear refractive index.
Sugandha, please try to complete fast.
Yes, sir. So for device fabrication, it is very important to know the thermal effects as they contribute to various effects like making the optical limiting properties better. So that's why this study is important. This also helps in generation of a dark core beam, which is the reference is given here. Thank you.
You have using that sulfuric acid as a medium.
Sir, actually, our main is DBPI dye and it is dissolved in sulfuric acid. So absorbing medium is DBPI dye and the solvent.
The dN by dt value of a sulfuric acid is how much?
Sir, it is around, actually, for this study, we have not included the dN by dt value because we have just found the delta T. We have not gone into the finding the non-linearity of the material.
No, the
yet.
dN by dt value will give you that whether the beam is try to focus it or diverge it.
Yes, sir, but
after passing through the sample.
yes, but for the simulation, we have not yet included it.
Okay.
I have one question.
Yes,
You are
sir.
using femtosecond pulses, right?
Yes, sir. Femtosecond as well as picosecond.
Okay, so that will lead to ablation also. Means it will go into
Yes.
vapor state.
Yes,
So
sir.
it will lead to ablative cooling also. So have you incorporated that effect?
No, sir. For now, we have not.
Okay.
Thank you, sir.
So if the question answer is over, then I would like to thank our esteemed judges for evaluating altogether 21 number of posters in this session. And also we would like to thank all the presenters for their active participation and presenting their work in NLS-30. So now we will break for a tea and return back to attend the next session that is going to start at 16:45 hours. And special thanks to Dr. DJ Biswaji for joining as a panel in the judges for in the last moment. Thank you, sir.
Thank you. No mention. So what about that evaluation? Shall we discuss amongst ourselves and finalize? I don't know what would be the
Sir, we cannot, I guess, because some students are here and your mic is on.
Okay. Okay.
Actually, that we will send some table, that whatever table Dr. Padma Madam has sent to us, we'll fill that table.
Okay, I will give it to her.
Ravaji,
Yeah.
Ravaji, please switch off your mic. देखिए और कौन कौन है, सबको एग्जिट हो गए क्या? वो स्टूडेंट्स?
I think all have exited.
Excuse me, sir. You may connect using mobile phone to other judges and discuss.
Okay.
Or sir, we will send you that list. Some
Okay.
and give us.
जाके उधर जाके बालाजी बोल दीजिए.
Okay, that would be better.
Mukhopadhyay, sir. Yes. Particular take.
So
Hello.
So should I mail it or?
Wait, that was I also telling. That should we mail this? That